The pen is mightier than the sword. In the world of warfare, this means better technology always beats brute force and sheer gunpowder. The Nazis knew this and spent a great deal of effort and money into weapon development and scientific research. This resulted in incredible technological advances in every field possible, something that was never achieved during peacetime. Incredibly fast ships, almost undetectable airplanes, ballistic missiles capable of reaching space, new materials, and some of the most destructive weapons in history were some of their achievements. They even came very close to developing the atomic bomb. It was only because the Americans snatched their most important scientists and stole the Nazi scientific research that Germany did not win the war. Welcome to the Marshall Memoirs. Before the war, the Versailles humiliation. World War I officially ended when the Allied powers and Germany signed the Treaty of Versailles on June 28, 1919. Although it was presented as a fair contract between sovereign nations, the true objective behind it was to punish Germany for starting the war. In this sense, it sought to definitely disarm Germany by imposing a series of restrictions to its military and financial power. The weak Weimar Republic that emerged after the war had no choice but to sign it. In general, the Treaty of Versailles can be divided into three main areas: military restrictions, territorial losses, and financial reparations. For example, the German army was capped at 100,000 men. This was an extremely small dotation, considering that by 1939 the British army consisted of more than 1 million men. Also, Germany was not allowed to have an air force of any kind, or any seaworthy vessels larger than 10,000 tons of displacement. American and British destroyers often doubled that amount, making these limitations seem like an unfair humiliation in the eyes of the German people. Regarding occupied land, Germany was forced to make several territory concessions to France, Belgium, Poland, Czechoslovakia, and Denmark. The size of the country was thus considerably diminished, often separating entire families that lived in the same region for many generations. They were also forced to give up their overseas colonies in Africa and the Polynesia. In Africa, the German Empire once controlled German East Africa, now Tanzania, German Southwest Africa, now Namibia, Togo, and part of Cameroon. In the Pacific Ocean, it had Micronesia, Nauru, and Samoa, as well as part of the island of New Guinea. Finally, the treaty famously included a war guilt clause, which stated that Germany had been the sole responsible party for starting the war. This allowed the winning nations to receive compensation in terms of reparation for war damages. The treaty was so harsh that the 1920s were a period of serious economic instability in Germany. This in turn allowed figures like Adolf Hitler to make plans for returning Germany to its former glory. So when Hitler came to power in 1933, he knew he had to find a way around these restrictions if he wanted to develop a powerful army with which to conquer Europe. On May 1, 1934, he appointed Bernhard Rust as Reich Minister of Science, Education and Culture. Rust was charged with the responsibility of leading science in the spirit of party ideology and preparing for war. Most Jewish teachers and scientists were expelled from the main universities in the country, and considerable funding was funneled into the development of weaponry and new technologies that could be used for warfare. Of course, this did not go unnoticed in the rest of Europe, and the main powers of the continent grew increasingly preoccupied with the development of the new Nazi army. At first, they strictly followed the Treaty of Versailles, but towards the end of the 1930s, Hitler ordered that the treaty was disregarded, marking the start of a frenetic weapons race. As a response to German rearmament in violation of the Treaty of Versailles, French Defense Minister ordered that a line of defense was built along France's border with Switzerland, Germany, and Luxembourg. The so-called Maginot Line was built between 1929 and 1939 and consisted of a complex network of fortresses, bunkers, obstacles, and artillery positions along France's border with Switzerland, Germany, and Luxembourg. The line was only partially extended north of this, because it was assumed that any future German invasion attempt would be met and defeated in Belgium, hopefully with British assistance. In May 1940, Nazi Germany invaded Belgium. The main focus of the German attack was through the Ardennes forest, which was mostly undefended. The Maginot Line was quickly outflanked, and French forces caught off balance by the speed of the German advance. Within 6 weeks, France had surrendered to German control. Testing new technologies, the Battle of the River Plate. On December 17, 1939, just 2 months after the start of World War II, an unexpected explosion was heard throughout the peaceful cities of Buenos Aires and Montevideo. They are separated by the River Plate, the widest river in the world, and from both shores a column of smoke could be seen in the middle of the river. A few minutes later, there was nothing. The German pocket battleship Admiral Graf Spee had disappeared beneath the waters of the river, scuttled so that Allied scientists could never get their hands on the ship or her amazing technology. 3 days later, in the Immigrants' Hotel of Buenos Aires, her captain carefully laid a German flag in his bed, lied on top of it, and shot himself with his officer's Mauser pistol. Captain Hans Langsdorff had been appointed to the Graf Spee in 1936, but he already had an extensive career in the German Navy by that time. He had entered the Naval Academy against his parents' wishes in 1912 and became a war hero during World War I. But nothing he had seen in all his years in the Navy could prepare him for the technological marvel that was the Graf Spee. More than a ship, it looked like a space rocket out of a science fiction novel. She was simply the most advanced craft in the world at the time, which was a miracle, considering the limitations imposed by the winners of World War I less than 20 years before. Hitler's best engineers were tasked with building the best, most destructive craft, and rapidly they brought him the plans for a new type of destroyer. It was so powerful and compact that he could not believe it was possible. They called the prototype a Taschenkreuzer, or a pocket cruiser, because of how small it was. But while they did not look like much from a distance, the German pocket cruisers were incredibly swift and deadly, reaching speeds of almost 30 knots, or 50 kilometers an hour, thanks to their 54,000 horsepower diesel engines. The ships were fitted with a catapult, allowing a small Heinkel He-60 floatplane to lift off directly from the ship's deck. Admiral Graf Spee was also the first German warship to be equipped with a radar, a technology that had been invented only 1 year prior by a British team of scientists. The Nazis were quick to copy the technology and learn how to make their own radars. While not a Nazi himself, Captain Langsdorff was above all loyal to his country. For this reason, he followed his superiors' orders without questioning. When Germany declared war on Britain and France, the Graf Spee was at sea, patrolling the Indian Ocean. From that moment on, whenever a British merchant ship was spotted, Captain Langsdorff ordered his crew to sink them, but making sure that no crew was harmed in the process. Afterwards, the enemy's crew would be dropped at the nearest port. After sinking several enemy ships, the Graf Spee sailed to the Canary Islands for replenishing supplies. Then she continued to sail the South Atlantic Ocean. On the 13th of December, the Graf Spee spotted a group of 3 British destroyers several miles east of Montevideo, Uruguay. They were identified as the Exeter, the Ajax, and the Achilles. The British Navy vessels were the first to fire, but they missed. Graf Spee retaliated with an accurate opening salvo, which severely damaged Exeter. After 2 more hits from cannon and torpedoes, she had to flee the battle in order to be repaired. Knowing that the Graf Spee had more weapons but was only 1 ship, Ajax and Achilles split and tried to surround Graf Spee. An unlucky 8-inch shell fired from Achilles penetrated 2 decks of the Graf Spee and completely destroyed her raw fuel processing unit, which meant she could not go very far before needing to replenish fuel. However, she gave a fierce fight and both Ajax and Achilles took heavy damage. Captain Langsdorff ordered to retreat towards Buenos Aires, but they were denied shelter by the Argentinian authorities. The Graf Spee then crossed the River Plate towards the port of Montevideo, but there, the captain was informed that they would only allow them to stay for 48 hours. This was not enough time to refuel and repair the hull and the fuel unit, so he made the only choice a respected mariner could make. He sailed the Graf Spee to the middle of the river, placed a few explosive charges, and abandoned ship with all his crewmen. Then he blew her to pieces, making sure that her cutting-edge technology would not fall in the hands of the Allies. Terror under the sea, submarine warfare. Although impressive, the Graf Spee was just one of the many inventions that helped Germany rule the seas, at least at the beginning of the war. And while submarines were not a new invention, as they had been around since the early 1900s, it was during World War II that they were transformed into true killing machines. From midget submarines to the classic and stealthy Mark 21 U-boats, More than 1,200 submarine craft were built between 1939 and 1945. No sea in the world was safe anymore for the Allied ships. From September to December 1939, German U-boats sank 221 ships, only losing 9 U-boats in the process. This impressive feat was achieved under the direction of Grand Admiral Karl Dönitz, one of the best war strategists and a proficient submarine pilot who had commanded several of this craft in World War I. Dönitz became famous for his Wolfpack strategy, consisting in several U-boats attacking a single target at once. This was extremely efficient, but also required a large number of craft in service. The combination of Dönitz's masterful strategy and several technological advancements made German U-boats lethal predators around the world. First of all, new hull welding techniques and improved steel allowed for deeper dives. This meant more chances of being undetected by enemy ships. German U-boats in World War II were also equipped with passive detection sensors which were ahead of their time and the competition. And finally, they had superior weapons. For example, the electric G7E torpedo costed half as much as a conventional torpedo, and thanks to its engineering did not leave a trail of bubbles. This type gave the U-boat an advantage in a daylight attack. On August 27, 1941, the Royal Air Force Coastal Command's 269 Squadron performed a remarkable mission, something never repeated during the war. They captured a U-boat, unassisted by surface ships. This was U-boat U-570, which they promptly took home to Britain in order to be reverse-engineered. The engineers that examined U-570 were astounded and came to the conclusion that every piece of equipment it had was superior to the Royal Navy's, including better attack periscopes and a surface night sight that allowed to see practically in complete darkness. Immediately, they started incorporating the Nazis' technology to their own craft, which soon became much more powerful. However, they still needed to counter Dönitz's Wolfpack strategy. They did so by forming so-called hunter-killer groups consisting of fast anti-submarine escorts and aircraft carriers. The purpose of naval operations changed from avoiding U-boats and safeguarding convoys to seeking them out and destroying them wherever they operated. Dönitz reacted by deploying his U-boats near the Azores, where land-based aircraft still had difficulty reaching them. In this region, he hoped to threaten the Gibraltar-Britain convoy route. Dönitz intended to concentrate his power in a rough arc from West Africa to South America and the Caribbean. But most of the 39 U-boats deployed on these operations were intercepted and destroyed. It was a sad end for one of the greatest submarine fleets in history. The German Kriegsmarine also invented a type of midget submarine called Biber, which is German for beaver. This was a one-person craft intended for attacking coastal enemy shipping vessels. The beavers were equipped with 2 externally mounted 53 centimeter or 21 inches torpedoes or mines, and were hastily developed towards the end of the war to help meet the threat of an Allied invasion of Europe. This resulted in basic technical flaws that, combined with the inadequate training of their operators, meant they never posed a real threat to Allied shipping, despite 3 24 submarines being delivered. One of the pilots appointed to a midget submarine was Joachim Langsdorff, the son of Captain Hans Langsdorff. Death from above, the deadly Messerschmitt Me-262. Among the most promising projects the Minister of Science evaluated was a patent presented by a young physicist named Hans von Ohain. By 1935, when he was only 23 years old, he successfully designed a turbojet engine that could be fitted to aircraft. He was assigned a team of specialists as well as a big budget, so he could design and test the world's first jet aircraft, the Heinkel He-178. The He-178 proved very helpful in the invasion of Poland that year. So von Ohain's team started making plans for more advanced jet fighter airplanes. These plans were given the codename Project 1065 and were labeled as top secret. The Ministry of Aviation requested that they engineered a jet aircraft capable of at least 1 hour of endurance and reached a speed of at least 850 kilometers per hour or 530 miles per hour. The initial plans for the Me-262 were drawn up in early 1939, but the original design was very different from the aircraft that eventually entered service. The successive changes to the design and several problems with the jet engines resulted in great delays to the first prototype. Originally designed with straight wings, Problems arose when the engines proved heavier than originally promised. While waiting for the definitive engines, the manufacturing company Messerschmitt moved the engines from the wing roots to underwing pods, allowing them to be changed more readily if needed. This proved an excellent design choice, but unfortunately came too late into the war. Experts agree in that the Messerschmitt Me 262 was without a doubt the best fighter plane of World War II, bristling with firepower and capable of flying 200 kilometers or 120 miles per hour faster than the American P-51 Mustangs. It had a sleek, elegant design and had outstanding maneuverability. The only problem was that it was introduced into combat too late in the war. The Messerschmitt Me 262 was delayed multiple times because the Junkers Umo 004 jet engines that powered it could not reach quantity production until the spring of 1944. The Ministry of Aviation did not assign the priorities necessary to put reliable jet engines into production until it was too late. For this reason, out of the more than 1,400 Me 262s built by Germany, about 300 ever saw combat. Still, the Me 262 was the only jet fighter to see air-to-air combat in World War II, and its sight was feared by both Allied jet fighters and bombers. The jet fighters simply could not retaliate, and the slow bombers were obliterated by bursts of the Mk 108 cannon fire fitted to the Me 262. But the jet engines that could have easily won the war for Germany were never mass-produced, and Allied intelligence calculated that there were probably never more than 36 Messerschmitt Me 262s in the air at a time. This was almost nothing compared with the thousands of Allied bombers and fighters that flew over the ruins of Germany in 1945. By this time, Allied nations had developed excellent fighters like the Spitfire 9, the P-47D, and then in 1944 introduced the Tempest, Spitfire 14, and P-51 Mustang. Alien technology, the flying wing. In the last months of World War II, Nazi Germany began testing an experimental fighter that looked more like a spaceship than an aircraft. The Horten Ho 229 did not only look futuristic, but was outfitted with the best technology available in the world. The most notable difference with all the other airplanes was the lack of a tail vertical stabilizer. By getting rid of the tail, which usually helps keep the aircraft stable and prevents it from yawning from side to side, the aircraft was a lot harder to control, but also it made the plane almost invisible to the radar. Their concept looks more like a flying saucer than a fighter plane, and for this reason it was commonly known as the flying wing. This design helps reduce the aircraft's size while at the same time creating a smoother, more aerodynamic shape that could not easily be spotted in the radar. The Horten Ho 229 was so far ahead of its time that its secrets are still not completely understood. Scientists at NASA are still working on a captured prototype to discover just how its creators managed to overcome the considerable aerodynamic challenges that should have made it unflyable. The secret was in its bell-shaped wing, which cancelled out the yawning issues from not having a tail. This was a genius design because it also reduced drag, helping the stabilization of the plane and greatly reducing the fuel consumption while allowing it to fly faster. The Ho 229 was developed by two brothers, Walter and Reimar Horten, who were among the best aircraft engineers not only in Germany but the whole world. In the late 1940s, the personnel of Project Sign, the US Air Force's investigation on the existence of UFOs, seriously considered the possibility that many sightings could have been secret aircraft manufactured by the Soviets based on the Hortens designs. The Hortens began designing aircraft in the early 1930s, while Germany was officially banned from having an air force under the constraints of the Treaty of Versailles. However, military pilots and engineers still clandestinely met at sporting air clubs as a way to get around such restrictions. This is where the foundations were set for what was to become the Luftwaffe, Nazi Germany's air force. In these clubs, the Hortens met unconventional aircraft designer Alexander Lippisch, who was a pioneer of delta-wing aircraft designs. The Hortens developed their flying wing approach with increasingly effective results, ending in their Horten Ho 4 glider, in which the pilot lay prone in the aircraft, which meant the cockpit canopy did not protrude from the fuselage and thus did not create aerodynamic drag. By the time the Ho 4th glider was being tested, Walter Horton had already served as a Luftwaffe fighter pilot during the Battle of Britain in 1940. This battle was won by the British, but for Walter Horton it was a turning point. He realized Germany needed a new kind of fighter aircraft. So once back on land, he began to discuss with his brother the possibility of designing an all-wing aircraft. At the same time, the head of the Luftwaffe, Hermann Göring, had requested designs in a project called 3X-1000. He wanted to develop aircraft that would be able to carry a 1,000 kilograms bomb load 1,000 miles, 1,600 kilometers at 1,000 kilometers per h, 625 miles per hour. That led the Hortons to develop what would eventually become the Ho 229 prototypes. The first of the 3 prototypes was an unpowered glider built to test the aerodynamic design. The second added jet engines and flew successfully on the 2nd of February 1945, though it crashed after engine failure on another test flight a few weeks later, killing its test pilot. This proved that the aircraft indeed could take off, cruise and land. Rocket science, Hitler's vengeance weapons. Regarding the war on land right from the beginning of the war, Hitler ordered the development of what he called vengeance weapons. They were codenamed V for their name in German Vergeltungswaffen. The objective of the V project was the strategic bombing of enemy cities, specifically from a long range. Only the V1 and V2 were used during the war, but they proved highly deadly, killing as many as 18,000 people in total. The V1 flying bomb was an early prototype of cruise missile, which could adjust its trajectory while on the air. It was nicknamed Hellhound by the Germans and Buzz Bomb by the Allies. Its development began in 1935, when Paul Schmidt and Professor Georg Hans Madelung submitted a design to the Luftwaffe for a flying bomb. It was an innovative design that used a pulse jet engine, and on the 27th of February 1942, Goslau and Robert Lusser sketched out the design of an aircraft with the pulse jet above the tail, the basis for the future V1. Lusser produced a preliminary design in April 1942, which used gyroscopes for guidance. Its specifications included a range of 299 kilometers or 186 miles, a speed of 700 kilometers per h or 435 miles per hour, and capacity for delivering a half-ton warhead to a faraway target. On the 26th of May 1943, Germany decided to put both the V1 and the V2 into production. In July 1943, the V1 flew 245 kilometers and impacted within a kilometer of its target, proving its incredible accuracy. The Wehrmacht, or German Army, first used the V1 missiles against London on the 13th of June 1944, 1 week after the successful Allied landings of D-Day. At peak, more than 100 V1s a day were fired at southeast England, totaling 9,521. After it became evident that there was no way of winning the war in Britain, the Germans directed V1s at the port of Antwerp and at other targets in Belgium, launching a further 2,448 V1s. The attacks stopped only a month before the war in Europe ended, when the last launch site in the Netherlands was overrun on March 1945. The V2 rocket was, by all means, Germany's most advanced weapon of the Second World War, but also the most wastefully expensive. It was an enormous ballistic missile carrying a 1-ton warhead, which reached the edge of space before descending at supersonic speed to its target. This meant that nobody at the target could hear it coming until it exploded. It was powered by a liquid propellant rocket engine specifically developed for this type of rocket, and so advanced that its engineers deeply regretted that it was completely destroyed after just one launch. German rocket development began before the war, but the V2 was not ready until the autumn of 1944. It was used mainly against London and Antwerp, and there was no defense against it. However, although technically brilliant and of undoubted propaganda value to an embattled Nazi hierarchy, the weapon inflicted comparatively little damage in return for the vast sums spent on it. The total quantity of explosives delivered by the 3,000 or so V2s fired was far less than could be dropped in a single raid by RAF Bomber Command. 9,000 people were killed in V2 attacks. Instant death at everyone's hands. The world's first assault rifle. Nazi scientists developed every kind of gun imaginable, from the biggest cannons and rockets to small handguns. But perhaps the most enduring and innovative field combat weapon developed during World War II was the Sturmgewehr 44, or STG-44 for short. It was designed as a link between a rifle and a machine gun, but at the same time it was portable and light. This makes the STG-44 the first assault rifle in history. It was fitted with a long cartridge and a more compact design compared to a battle rifle, with a higher rate of fire. The Wehrmacht first had to fight against great numbers of semi-automatic weapons during the invasion of the Soviet Union in 1941. Increasing numbers of semi-automatic Tokarev, SVT-38 and SVT-40S were used by the Red Army, while some Soviet rifle companies were completely equipped with PPSH-41 submachine guns. The key was the sheer quantity of factories working round the clock to provide ammunition to troops in the Western Front. Germany hoped to be able to reach a similar production rate thanks to the new factories in Austria, Czechoslovakia, Poland and France. In Russia, after experiencing high volumes of automatic fire from soldiers wielding Tokarevs, German commanders rethought their small arms requirements. The German army had been attempting to introduce semi-automatic weapons such as the Gewehr 41, but these proved troublesome in service and production was insufficient to meet requirements. Several attempts had been made to introduce lightweight machine guns or automatic rifles, but recoil from the powerful Mauser rifles was too difficult to control in automatic fire. By changing the ammunition used and the way of feeding it into the chamber, the muzzle impulse was reduced. This allowed the STG-44 to offer its user useful automatic fire within actual ranges of combat, a feature that is widely regarded as the most important advance in small arms since the invention of smokeless powder. But the rate of fire was not the only problems faced by German troops in Russia. The winter of 1941 proved to be a nuisance because the lighting mechanism of the German flamethrowers was unable to cope with the cold weather conditions. This prompted innovation, and later versions of the weapon replaced the hydrogen torch with a cartridge-based system which proved more effective in cold weather. The standard model of flamethrower used by the German army in World War II was the Flammenwerfer 41, or FMW 41. Its production began in 1941, being an upgraded version of the earlier FMW 35, whose main issue was that it was too heavy to carry for long periods of time. Model 41 was much lighter, with a total weight of 18 kilograms. The intended use of such weapons was to clear enemy trenches and buildings in highly fortified areas. From 1942 to April 1945, more than 64,000 Model 41 flamethrowers were produced, but were discontinued right after the war. Similar to many other designs of the time, the FMW 41 used a hydrogen torch that ignited a mixture of tar and petrol, which was fired from a handheld torch attached to a tank. The petrol and propellant were carried in separate tanks carried on the back of the operator, with each tank carrying up to 11.8 liters of a tar and petrol mixture called Flamol 19. It was more reliable and easier to operate than its predecessor, and it had an increased range of 32 meters or 105 feet. War technologies for everyday use. Perhaps what was innovative about the FMW 41 was not so much its design or its engineering, but the composition of the fuel mixture developed in the tragically famous IG Farben, the same company that mass-produced the chemicals used in the gas chambers at Auschwitz and other death camps. IG Farben scientists made fundamental contributions to all areas of chemistry and the pharmaceutical industry. Otto Bayer discovered the polyaddition for the synthesis of polyurethane in 1937, and 3 company scientists became Nobel laureates: Carl Bosch and Friedrich Bergius in 1931 for their contributions to the invention and development of chemical high-pressure methods, and Gerhard Domack in 1939 for the discovery of the antibacterial effects of Prontosil. IG Farben also developed a patent that is used to this day all around the world. They discovered a method for making synthetic rubber, which was very useful during the war when access to rubber plantations in Asia and America was very difficult to achieve. They later sold the patent to the American company Standard Oil, which allowed the United States to ensure the production of artificial rubber in a short time and meet its needs in the future, especially when fighting against Japan. Many other everyday activities were improved thanks to the scientific developments of Germany during the 1930s and 1940s. Hans Busch invented the first electromagnetic lens in 1926, and thanks to this invention, Ernst Ruska and Max Knoll, a physicist and an electrical engineer from the University of Berlin, created the first electron microscope in 1931. This prototype was able to produce a magnification of 400 power and was the first device to show what was possible with electron microscopy. In 1933, Ernst Ruska developed on the original model further to develop an electron microscope that was capable of producing an image of higher resolution than what was possible with optical microscopy. This completely revolutionized the field of microbiology, allowing for several advancements in disease control. In 1937, Manfred von Ardenne developed the first scanning electron microscope. Nazis also engaged in more academic work. For instance, they financed an important archaeological excavation in the Greek site of Olympia. Granted, it had mostly political reasons. For Hitler and the active members of the Nazi Party, the excavations carried out at Olympia on the eve and in the aftermath of the 1936 Olympic Games were primarily aimed at historically appropriating the renowned ancient site and celebrating the Hellenic-Germanic relationship. According to Nazi ideology, the Greeks were descendants of the ancient Aryans, just as the Germans were. Hitler even instructed the Reich's architect Albert Speer to construct a huge stadium at Nuremberg that could seat 400,000 people, so that the Olympic Games could be held there perpetually every 4 years. But regardless Hitler's autocratic fantasies, the truth is that the site of Olympia had been neglected for years, and the generous funding that he sent to the German Archaeological Institute in Olympia allowed for the first systematic and scientific excavation of the site, under the direction of Emil Kunze and Hans Schleif. The excavations came to a halt in 1940, and shortly after the country was invaded by Germany, which was tragic for all the rest of the archaeological sites in the country. Thunder on the Iron Road, Germany's railway guns. Unlike synthetic rubber and polystyrene, railway guns had very specific uses and capabilities. For once, they could only reach places where a railroad was laid down before. This is the main reason why they made so few of them. The biggest railway gun the Germans ever built was called Schwerer Gustav, and a second gun was supposedly built that was nicknamed Dora. To this day, there is no evidence of Dora's existence, although it is believed that it was the gun used in the siege of Stalingrad in 1942. Schwerer Gustav was, and still is, the biggest piece of artillery to ever be used in combat. This behemoth was almost 50 meters in length, 7 meters wide, and the barrel alone measured 32.5 meters. It shot enormous cannonballs, 80 centimeters in diameter, which could reach a distance of 47 kilometers, or 30 miles. It took 250 people 3 days of work to assemble the giant cannon, and usually 2 flak battalions were deployed in its proximity to protect the gun from enemy air attacks. As the French were digging the Maginot Line, in 1934 the German Army High Command commissioned the Krupp Company to design a gun that could destroy the forts of the Maginot Line. The gun's shells needed to be quite heavy in order to punch through 7 meters of reinforced concrete or 1 full meter of steel armor plate from beyond the range of French artillery. The size and weight of such a monstrosity meant that it could not run in common railway tracks, but needed a special twin set of tracks to take it to the French border. Special locomotives and cranes were transported as well, so that the gun could be positioned properly. However, construction of Schwerer Gustav did not start until mid-1937, when Hitler personally gave the project green light. Technical complications in the forging of such massive pieces of steel made it evident that it would take several years to complete the first gun. A second gun, Dora, was commissioned, but its fate is unknown. By the time Krupp had finished building Schwerer Gustav, France was long since a territory of the Third Reich. But it was still useful in the Eastern Front, so in March 1942, it was assembled and taken along the twin railroads towards Crimea. The train carrying Schwerer Gustav was 25 cars in total. That means the whole train was 6 kilometers or 1 mile in length, only to carry a single gun to the front. The first time Schwerer Gustav was used in combat was during the siege of Sevastopol in June 1942. By the end of the siege on the 4th of July, the city of Sevastopol lay in ruins. and 30,000 tons of artillery ammunition in total had been fired. Gustav had fired 47 rounds and worn out its original barrel, so a spare barrel was brought to replace it while the original one was sent back to Krupp's factory for refitting. After the siege, the gun was dismantled and moved to the northern part of the Eastern Front, where an attack was planned on Leningrad. The gun was placed 30 kilometers or 18 miles away from the city, but the attack was cancelled before it could be shot. The German army abandoned the gun near Leningrad during the winter of 1942-43. On the 14th of April 1945, one day before the arrival of US troops, Schwerer Gustav was destroyed to prevent its capture. Another interesting large cannon was the so-called Karlgerät. Like Gustav and Dora, it was transported on railroad tracks, but only across short distances. As it was considerably lighter than Gustav and Dora, it could be disassembled and assembled by a small crew in a single day. However, with its 60-centimeter, 2-ton ammunition, it was equally as destructive. The main difference with those, apart from its size and weight, was the fact that it was self-propelled, so it did not rely on a locomotive pulling it. 7 guns were built, 6 of which saw combat between 1941 and 1945. It was used in attacking the Soviet fortresses of Brest-Litovsk and Sevastopol, bombarded Polish resistance fighters in Warsaw, participated in the Battle of the Bulge, and was used to try to destroy the Ludendorff Bridge during the Battle of Remagen. World of tanks, Germany's best field weapons. While in most fields the Allied forces had at least as good weapons as the Germans, the Third Reich absolutely dominated regarding tank design and production. They produced the best, most advanced tanks, and at a higher rate than anybody else. But what is key in this aspect is the fact that already before the war they had started building thousands of panzer tanks, mostly Panzer I and II. During the war, more advanced models were developed and mass-produced, arriving to a total of 50,000 tanks made in Nazi Germany. Most of these were the mighty Panzers, the Thuren and the Four, medium tanks with an impressive endurance and autonomy. Unlike Britain, which produced a variety of mediocre designs, the German Panzers relied essentially on 3 types: the Panzer IV, V, and 6, each one excellent for its specific purpose. Many German tanks used diesel fuel, which gave their crews an excellent chance of surviving battle damage, in contrast to the American Sherman with its gasoline-powered engine. Shermans caught fire more easily, usually killing the whole crew in the process. The Panzer IV was the most common German World War II tank and featured prominently in the defense of Normandy. A more advanced version of the Panzer III, more than 8,000 of this single model were built. Designed in 1937, the early models were armed with short-barreled 75 mm guns best suited for infantry support. However, its combat experience, and especially in Russia, demonstrated the need for more velocity and for achieving greater penetration of enemy armor. Therefore, a long-barreled gun was added. The resulting Mark IV-G became the third main variant, appearing in 1943. It weighed 25.5 tons and was powered by a Maybach 300 horsepower engine delivering a top speed of 25 miles per hour. The 5-man crew was protected by 30 to 80 millimeters of armor and had a standard load of 87 main gun rounds. The Panzer V is usually regarded by war history enthusiasts as one of the most attractive tanks of all time, but it also incorporated German wartime experience in its design. Its notoriously sloping armor was calculated to deflect enemy rounds striking at any angle. With 40 to 80 millimeters of armor and a high-velocity 75 mm gun, the Mark V was a formidable opponent on any front. Though unusually heavy for its day, at some 50 tons, which was about twice as the Mark IV, the Panzer V was reasonably fast clocking at 25 miles per hour. But what really separated it from the rest was its cruising autonomy of 125 miles on roads. These tanks were deployed in time for the Battle of Kursk in Russia during the summer of 1943, but experienced mechanical problems there. Subsequent improvements were made to the suspension and transmission, and some 5,000 Panzer V-S were ultimately produced. Finally, the Panzer VI, also known as Tiger, was the definitive German tank. Appearing in 1942, it was a 62-ton Land Cruiser with the awesome 88 mm cannon that was already feared and respected by the Allies. The gun was extremely accurate, Reportedly, it could place 5 rounds within 18 inches of each other at 1,200 yards. The Tiger was protected by 62 to 102 millimeters, 2.4 to 4 inches of armor, rendering it almost impervious to conventional anti-tank weapons. It had the same basic engine as the Mark V, which produced a respectable road speed of 25 miles per hour and about half as fast cross-country. Despite their strengths, Tigers were expensive to produce, so only 1,340 were made. They were issued to only company and occasionally battalion-sized units. Failed futuristic experiments. Not every Nazi invention was a success in the battlefield. The Nazi Ministry of Propaganda began talking about Wunderwaffen, literally meaning wonder weapons, and the term was applied to most new inventions in order to boost confidence in society. Most of these super weapons, however, were never produced and only remained prototypes, or if they did take part in combat, it was either too late or in too insignificant numbers to have a military effect. The Panzerkampfwagen Maus, designed by Ferdinand Porsche, was the ultimate expression of Hitler's desire to produce an indestructible super-heavy tank. It was first proposed in 1942, but few in the German High Command saw the need for this 200-ton monster, almost 3 times as heavy as the heavy Tiger tank. Trials began in 1943, but there were constant mechanical problems associated with the drivetrain. The tracks were driven by electric motors, but its top speed was barely 12 miles per hour. The Maus had armor up to 240 mm thick and a 12.8 centimeters gun. Although there were plans to build 150 tanks, only 2 prototypes were ever completed. The V3, the third Vengeance weapon, was a supergun designed to bombard London from an underground complex 100 miles away at a town near Calais in northern France. The V3 was constructed on a multi-chamber principle, whereby secondary charges firing in sequence along the main barrel accelerated a shell to the velocity required to reach its target. 25 gun tubes were sunk into inclined tunnels in the ground, further protected by a vast concrete slab. It was planned to attack London at a rate of 600 shells an hour. The Allies assumed the site was part of the V2 rocket program and launched bombing attacks in late 1943. Despite intense work by the Germans to finish the project, it was finally put out of action by a raid on the 6th of July 1944 before a single shell had been fired. Another vehicle, codenamed Goliath, was a German expendable miniature tracked vehicle designed to deliver an explosive device by remote control. There were 2 types, battery-powered, with a 60 kilograms charge, or a larger petrol engine version that could carry a 100 kilograms device up to 650 m from the controller. Goliath was to be used against buildings, bunkers, or even enemy troops and vehicles if the opportunity arose. Some were used to clear minefields. Unfortunately for the Germans, the trailing control wires were frequently cut, and the vehicle itself was slow and had poor ground clearance. 2,650 were built between April 1942 and September 1944, but were rarely effective. The Germans also experimented with larger radio-controlled vehicles that could drop a charge close to their intended target and then retire to a safe distance. But these, too, were a waste of resources. A very tiny and interesting plane, the Messerschmitt Me 163 Comet, was the world's only rocket-powered fighter. It was designed to intercept high-flying American bombers over Germany. It used a liquid propellant consisting of 2 volatile substances which ignited when mixed. Enough thrust was produced to propel the tiny fighter to an altitude of 39,000 feet in 3.45 minutes, with a top speed of over 550 miles per hour. Operations began in May 1944, but the Comet was almost too fast, and pilots struggled to engage the slow-moving bombers. Also, the rocket engine only had a burn time of 7 minutes, after which the pilot had to glide back to base. Accidents were common, and even small quantities of the highly unstable fuel could cause explosions if carelessly handled. The wind cannon was a bizarre German anti-aircraft weapon. It comprised a large barrel, bent upwards at one end, through which an explosive jet of compressed air was ejected upwards by the ignition of a mixture of hydrogen and oxygen. The aim was to knock down low-flying aircraft. Trials showed that a powerful shot of high-velocity air could inflict damage on ground structures, but it was unclear if it would have the desired effect against a small, fast-moving aircraft. In 1945, a wind cannon was installed on a bridge over the River Elbe, but it failed to achieve any results. The race for the bomb, Operation Paperclip. Ultimately, it was another technological advancement what allowed the Allies to win the war. They simply built the atomic bomb before the Germans could. This in turn had to do in part with the expulsion of Jewish scientists from Germany, many of which were leading figures in the theoretical and practical physics field. Apart from that, the Americans devised a secret operation aimed at bringing German and Austrian engineers, scientists and technicians to the United States after the end of the war. They desperately needed the manpower, as German scientists frequently led most fields in academia. One of the key figures in atomic research was Otto Hahn, a German chemist who was a pioneer in the fields of radioactivity and radiochemistry. He is known primarily as the father of nuclear fission. Hahn and his assistant Lise Meitner discovered radioactive isotopes of radium, thorium, protactinium and uranium in his laboratory at Magdeburg. In 1938, Hahn, together with Meitner and Fritz Strassmann, discovered nuclear fission, but only Hahn was awarded the 1944 Nobel Prize for Chemistry. Nuclear fission was the basis for nuclear reactors and, as the Nazi leaders soon discovered, nuclear weapons. Hahn also proposed that the best material with which to make both nuclear reactors and bombs was uranium. This was a rare mineral that was readily available in Czechoslovakian mines, which at the moment was occupied by Nazi Germany. Hitler ordered that the most elite scientists in the country, including Hahn, Werner Heisenberg, Hans Geiger, Carl Fried and others, were contacted and put to work in the development of nuclear technology. The Americans were terrified to learn of this incredible assembly of brilliant minds and thought Germans were close to developing a nuclear bomb. Operation Paperclip was put in motion in order to snatch some of Germany's best physics and bring them to American soil to work on the Manhattan Project led by J. Robert Oppenheimer. They even went as far as sending an armed man to a conference Werner Heisenberg gave in Zurich in 1943. The hitman had orders to listen carefully to the conference and to shoot Heisenberg only if his lecture indicated that the Germans were close to developing the bomb. It did not. Unlike the Manhattan Project, the German nuclear program was not geared towards a sole objective, but rather consisted in the funding and encouraging of the most gifted scientists so that they could develop their research in the best and most independent way. Several important milestones were achieved, like the development of methods for isotope separation, that is, for extracting only the molecules of a mineral that were radioactive. Also important was the work with moderators, materials that absorbed the extra neutrons that the radioactive materials expelled, thus preventing a nuclear explosion. German scientists were the first to recognize the moderating properties of heavy water, but unfortunately they did not consider graphite as a good moderator, probably because the graphite samples that Walter Botha used in his experiments were contaminated with boron. As the Soviets and Americans discovered shortly afterwards, graphite is one of the best moderators in existence, and also it is readily available in our planet. Nazi Germany physics never achieved man-made criticality, a prerequisite for developing a nuclear reactor and a nuclear bomb. They were very close, but an unfortunate and relatively unknown incident prevented them from achieving this milestone. The Leipzig experiment accident was indeed the first nuclear accident in history. It occurred on the 23rd of June 1942 in a laboratory which belonged to the Physical Institute of the Leipzig University. Scientists were manipulating what they called a uranium machine, a primitive form of research reactor, when there was a strong and unexpected steam explosion and fire spread around the laboratory. Fortunately, there were no fatal victims, like there were at the more widely known Demon Core incident at the Los Alamos Laboratory in New Mexico in 1945. Despite this last incident, Americans went on to find a way to artificially reach criticality, thus paving their way to the nuclear bomb and to definitely winning World War II. War is an unlimited source of horrors and destruction, but it has also been a powerful incentive for scientific advancements throughout history. Granted, most of the developments were geared towards finding more efficient ways of killing people. Bigger bombs, faster shooting guns, more enduring killing machines and farther shooting cannons were among these. But we must not forget that better ways of transport, new materials, and more efficient production processes were also developed thanks to World War II in Germany alone. And thanks to the war effort both in Germany and the Allied nations, the power of the atom could be harnessed. About 10% of the world's electricity comes from nuclear power, which is considered one of the cleanest forms of energy. This is a testament to those who gave their lives so that the new generations could live in a better, more free world.